Okay, this may take a while, but let's do all the little details of finding for 3 by 3 matrix, characteristic polynomial, the eigenvalues, the real eigenvalues, they're all real for this example, and the corresponding eigenvectors of this matrix here. Okay, so let's see. First, the characteristic polynomial is the determinant of A minus lambda times the identity matrix. Okay, here we'd have then the determinant of, let me skip a little bit of the details and not write everything out. We'll take negative 2 minus lambda I, that'll subtract lambdas along the diagonal of this matrix. Then we'll have to take a determinant. You got any shortcuts on determinants? Probably not row reduction stuff. The lambdas, whoops, I messed up there. The lambdas make it unrealistic to do row reduction. Okay, there we go. So here's A minus lambda I. Double check, make sure my entries are correct. Who's your favorite row or column? First row or second column, because they each contain 2 zeros. How about we go along the first row and expand the determinant, negative 2 minus lambda times the determinant of the associated minor matrix. Okay. Minus 0 times something plus 0 times something because of those other entries. I don't care what that something is, the product will be 0, but let me keep up the record there. And observe the alternating positive negativeness that we've advertised. Positive something, minus something, positive something. Okay. We could have expanded along the second column. Have to be probably a little extra careful with the positive and negative deal there along the second column. It'd read negative, positive, negative. That little negative 1 to the I plus j stuff we'd be dealing with. Okay, so we've got negative 2 minus lambda. Determinant, go down the main diagonal. That would give us negative 2 minus lambda times 3 minus lambda. The back diagonal, that'd be minus negative 5 times 0 minus negative 5 times 0. Okay, you want to multiply this out? No, you want to factor it because we're looking for zeros of it. So if you're multiplying out, be very careful and make sure that's something you definitely should be doing. So we get negative 2 minus lambda. Negative 2 minus lambda, 3 minus lambda, or negative 2 minus lambda squared times 3 minus lambda. They wanted the characteristic polynomial. There's your characteristic polynomial. Okay. They want the eigenvalues. We'll set that equal to 0. That'll give us the eigenvalues, and then it'll be off to the races to find the eigenvectors. Got a little bit of good news for you. Looks like it's only got 2 different eigenvalues. So we'll only have to find eigenvectors for 2 eigenvalues instead of 3 for 3 by 3 matrix. So that'll save us a wee bit of time. So we'll set the characteristic polynomial equal to 0, negative 2 minus lambda squared times 3 minus lambda. We'll set that equal to 0. And then the eigenvalues are lambda 1 equals, let's see, this would be 0 when lambda is negative 2. This would be 0 when lambda is 3. So we'll take lambda 1 equal to -2 and lambda 2 equal to +3. They wanted the eigenvalues. There's the eigenvalues. End sentence. Okay. So, I'd like to say we're halfway there, but we probably ain't halfway there yet. Now we need to find corresponding eigenvectors. Okay. To find eigenvectors, we consider the system of equations, the homogeneous system of equations, A minus lambda I equals 0. Times unknown vector, not quite room. Consider the system of equations A minus lambda I times vector V equals 0. Then vector V will be an eigenvector associated with corresponding eigenvalue lambda. So, homogeneous system of equations, excellent, always consistent, has a solution. The 0 vector is a solution to this. Can't use that for an eigenvector though, because eigenvectors by definition are non-zero vectors. So we need to go through and see what we get for different eigenvalues. Lambda 1 is -2. So consider the system of equations A minus lambda, would be -2, I times vector V, let's call it V sub 1, equals 0, putting a subscript on the vector because it's associated with lambda 1, if you will, the first eigenvalue. Okay. Consider this system of equations, or if we look at the associated augmented matrix, we'd have matrix A minus lambda I, so we get minus -2 along the diagonal. So we get these minus -2s. Be careful with the negative signs and using parentheses. Okay, we've got another -2 minus lambda 1 minus -2, 0, 0, 5, and 3. Minus -2. Okay, we're considering a homogeneous system of equations, so we'll augment that with zeros. Of course, those zeros on the right-hand side will never change, but I'm going to keep up with them anyhow. This is familiar territory. We just need to simplify this a little bit and probably do some row reduction. 2 minus -2, or sorry, -2 minus -2. This gives us a 0 there. First column otherwise is unchanged. 0, -2 minus -2 is another 0, like zeros. 5, 3 minus -2 is 5. Augmented with zeros. Matrix equality. We hadn't done any row reduction yet. How about we make some observations here? Let's see. We've definitely got one pivot-free column. We better have a pivot-free column. If you ain't got pivot-free columns, then you've got an invertible matrix and you've got a unique solution and you've done something wrong. There has to be multiple solutions to such a system of equations. All right, let's see. And I think I have a little copying error here. I got my script. I should have a -5. Should have had a -5 there. So let me correct that. Okay, and now a bunch of stuff's going to cancel out. Okay, so let's, how about we swap row 1 and row 3, creating a row equivalent matrix. Let's see, 5, 0, 5. Second row won't change. -5, 0, -5 when written correctly. Augmented with zeros. Okay. We're doing systems of equations again. We just spent a bunch of time doing determinants. Determinants change when I do row reduction, potentially. We're not doing determinants. We're doing systems of equations, row reduction stuff that we had dealt with earlier. We can got a couple of choices here. How about I take row 2 and add row 1 to it. Okay, so I'm looking at a pivot here, and I want to make zeros under it. Whoops, put a square around the pivot and circle the things I'll make 0. Okay, we've already got a 0 down there in that bottom entry of the first column. And then we'll divide by 5 to put this in reduced row echelon form in the next step. Do the addition here, we get a whole bunch of zeros. And just for the record, let's take row 1 and divide it by 5. To make the pivots 1, or the pivot 1. Okay. So, this is row equivalent to what we started with. And, hey, there's 2 pivot free columns. That's going to mean 2 free variables. Okay. We need to turn that back into a system of equations, which we'll solve. We'll introduce 2 free variables. And from that, we'll get the eigenvectors associated with this first eigenvalue. Okay. So, returning to a system of equations, we're looking for components of a vector. So let's call those components v1, v2, and v3. And that's been our standard notation. We want v1 plus v3 to equal 0. 0 equals 0, and 0 equals 0, so we really don't have that much information. Let's rewrite that as v1 equals, v2 equals, v3 equals. Okay, we'll get negative v3. v1 is negative v3. I don't know anything about v sub 2, so I guess v sub 2 equals v sub 2. Let's move this negative v3 over a little bit to align things. And I don't know anything about v sub 3, so I guess it equals v sub 3. So we'll have v2 and v3 as free variables. So we'll let, say, r equals v3 and s equals, how about r equals v2? Let's do it in a more logical order. R equals v2 and s equals v3 be free variables. Then we get v1 is negative s, v2 is r. Again, let me keep them sort of aligned. And v3 is s, where r and s can be any real numbers. Or, if you like writing this as vectors, I like writing this as vectors. We get that the vector with components v1, v2, v3, we'll recycle these symbols as components when we find the second eigenvector as well. The eigenvectors for the second eigenvalue. v1, v2, v3 is, how about r times a vector plus s times a vector. Coefficients of r are 0, 1, and 0. v1, v2, and v3 respectively. For s are negative 1, 0, and 1, where we can let r and s be any real numbers. We're picking out eigenvectors, so we can't use the eigenvector of 0. So r and s are real numbers, and not both r and s are 0. So here's the eigenvectors associated, sub 1, with the first eigenvalue. Let me double check my script to make sure my numbers are right. And let's do it again. Okay, don't forget to throw out the fact I can't have both of these 0, or else that gives a 0 vector. It's true up here, when I look at the system of equations, certainly R and S can be 0. But if R and S are both 0, we're getting, if I look back at the system of equations, we're getting the trivial solution back here. It's a solution to the system of equations, but it doesn't count as an eigenvector over on this side. Okay, lambda 2 equals, that other eigenvalue was 3. Same protocol. Consider a minus, in this case, we're taking 3, a minus 3 times I times some vector, let's call it vector v sub 2, equals 0. So, second eigenvector associated with second eigenvalue. I'm a little remorseful that I've used subscripted v's for vectors and subscripted v's as the components of those vectors. These are dummy variables. It's probably the cleanest way to do it, but it bugs me a little bit. Okay, so this becomes, or, let's see, matrix A, I'll copy from over here, replacing the negative 2's with 3's. So we'll have negative 2 minus 3, and then negative 5 and 5 for the first column. Second column will be 0, negative 2 minus 3, and a 0. Clean it up a little bit. Negative 2 minus 3, and the last column will be 0, negative 5, and 3 minus 3. We'll augment it with zeros because we've got in mind here a homogeneous system of equations. Okay, let's simplify it so I can fit it in. Negative 2 minus 3 is negative 5. Negative 5 and 5. 0. Negative 2 minus 3, still negative 5. 0. 0. Negative 5. And 0. Augmented with the zeros. Okay. There's a system of equations we need to solve. Doesn't look bad. A lot of 5's. We could get rid of those or do row operations. How about let's get rid of the 5's. Let's divide out 5's or negative 5's as appropriate. Going for putting it in reduced row echelon form. Check my script. I'm happy with those numbers. Okay, so let's take row 1 and divide it by negative 5. Let's take row 2, divide it also by negative 5, and row 3, let's divide it by 5. Okay, that'll produce the row equivalent 1, 0, 0, augmented with a 0. 1, 1, 1, augmented with a 0. 1, 0, 0, augmented with a 0. Nice. Okay, so how about we take this pivot of 1, use it to eliminate the stuff below, as we've often done. So that'll just be a matter of subtracting rows. We'll take row 2 and subtract row 1. We'll take row 3 and subtract from it row 1, giving, let's see, row 1 won't change, so go ahead and rewrite it. We're subtracting row 1, 1 minus 1, that'll be 0. 1 minus 0, 1 minus 0, 0 minus 0. Row 3, minus row 1, we'll get a 0. Actually get zeros in all the entries. Okay, and there you go. That's reduced row echelon form for this matrix. Okay, so let's turn that back into a system of equations. We've got a pivot-free column, and we got a free variable. Third column is pivot-free. You ain't got a free variable or pivot-free column, something's wrong. My guess always is you don't have the right eigenvalues. I mean, it could be something with the arithmetic, but if you don't have a free variable here, something's wrong. And we can rewrite this as we're taking those unknowns as v1, v2, v3 again. v1 equals 0, v2 plus v3 equals 0, and 0 equals 0. So there's the information from the matrix. Of course, we always want to rewrite that as v1 equals, v2 equals, v3 equals. Looks like v1 equals 0, v2 equals negative v3 from the second equation. v3, I don't know anything about v3, so v3 equals v3. Same amount as information as 0 equals 0. So we'll take v3 as the free variable. You knew that was coming because a third column was pivot free. So we'll let t equal v3 be a free variable. Okay, so I've chosen different letters for the three free variables, r, s, and t. Not that it really matters that much at this stage. Maybe in the next section it might matter a little bit. So it's a good habit to get in of using a variety of letters. You got a bunch of different free variables, which you will when you do this eigenvalue and eigenvector stuff. Use different letters. Okay, so that gives us v1 equals 0, v2 equals negative t, and v3 equals t, or writing it as we would for vector equation, the second vector with components v1, v2, v3 is of the form t times 0, negative 1, 1, where t is a real number, can't be 0 because this will be the eigenvalues. I'm sorry, the eigenvectors. So these are the eigenvectors. For the second eigenvalue of 3. Okay, so there's your one from beginning to end. We found the characteristic polynomial. We found its roots. That is, we found the eigenvalues of the matrix. There were 2 of them. It's a little unusual for a 3 by 3 matrix, but there were 2 of them. The first one had as its eigenvectors anything of this form. There's 2 linearly independent eigenvectors associated with that first eigenvalue. And there's 1 linearly independent eigenvector associated with that second eigenvalue. We didn't have 3 eigenvalues, but we did have 3 linearly independent eigenvectors. So I'm looking to kind of balance the books. We started with a 3 by 3 matrix. I expect to see 3s. I don't always see 3s, but this foreshadows some things we'll see in section 5.2 when we look at diagonalization. There's something kind of nice about this fact that there were 3 eigenvectors, linearly independent eigenvectors associated with a 3 by 3 matrix. Anyhow, there's your computations on finding eigenvalues and eigenvectors.